let's talk about you first.
Okay.
Why did you get into engineering?
Yeah, we can go as far as that. Well, why did I go in engineering? I guess that was I have the profile for it, for obviously.
Yeah.
I touched a computer when I was 11, and I started trying to. I first got interested into making websites, and since then I just learn and learn and learn. And yeah, engineering was just the obvious choice.
Right. So it wasn't because sometimes what happens is in my case, it was similar, but it was a different time. This was pre-computers, right? There was no PCs in my time. There were just valves and relays and transistors, right? So I actually met somebody, a group of guys actually in my neighborhood that were kind of into this kind of technology at the time, and that kind of got me interested. But I always wanted to be I wanted to be an astronaut actually when I was younger, rather than an electronics engineer. But I was asthmatic. I had suffered from asthma, and so medically I couldn't do that. So I was tinkering with mechanical stuff like taking engines apart and motor car engines, and when I was in my teens, and then I sort of gravitated towards radio controlled models, and then obviously into electronics. But it was a genuine interest. It's just curiosity for me. It was always about trying to learn how things work. That was the seed of my journey towards engineering. So okay, so what computer did you get then when you were 11?
Oh, I don't know. That was a family computer. I can't tell what it was. Too long ago. But what I did is I found I didn't know how that worked at all. So I was just searching stuff, and I was wondering what a website was. And I found this thing. At the time, it was called Angel Fire. It was a platform where you could like draw your website, put a button and like text box and those things. You could drag them or just add them to the page. And there was this advanced mode where you would see the HTML that it would generate. And I was like, I would make tests, putting a button, looking at the HTML code, trying to correlate what I was seeing with the code. And that's what got me hooked, I guess.
That sense of power, that sense of power. You click something, you do something in code, and you see a result, right? So it's that influencing the world around you, yeah.
Yeah, well, I think, yeah, really, I was driven by curiosity. I just had to understood how the thing worked.
Yeah, 100%. Okay, so obviously you went on to uni, and then
yeah.
So when you were
I'm
at
an
uni,
electrical engineer.
Yeah, so okay, you're electrical engineer. So you studied electrical systems, I guess, a lot of mathematics, control theory, and physics and material science, I guess, right?
Yeah. Well, where I live, we have between high school and uni, there's another school that you can go to, and they give technical course. So I have like a electronic technician course, also like soldering and all that. So I could have gone to the market as an electronic technician. Then after I did the electrical engineering, and I did half of a master in control theory, where I did the courses, but I didn't do the thesis actually, because I got kids, and that was a bit too much.
Okay, so let me ask you this.
Excuses.
No, well, that's fine. Because, when you're at university, you have the foundation year, which is just basic, physics and, electrical theory and so on. But eventually you will gravitate. There'll be some subject that you think, oh, this is really interesting. Were there any particular subjects that you did or topics that you studied that kind of really grabbed your attention?
Well, I always have been, not all, I won't say always, but I was really interested with all the DSP theory, even though I didn't have much opportunity to put that in practice. Well, I did put in practice the control theory, which has a big overlap with DSP, but it fascinates me. Well, just above you, there's a shelf with a bunch of DSP books that you can see.
Okay.
I like that stuff. It's
so DSP, so digital signal processing.
Yeah.
So, I mean, that has many use cases. Obviously, there's a lot in audio, right? They use a lot of that in audio, digital analog to digital, right? So did you end up applying that knowledge anywhere?
Yeah, like I said, it can be used when doing control, and I did work as a control engineer for a while. There are some applications when it comes to like pre-processing a signal that serves as an input to an algorithm, right? But I can't say that I went really deep like someone who works in radar would do, right?
Yeah.
So I put in practice, let's say, the introduction matter of those subject, but I did read on the deepest aspect of it just out of sheer curiosity.
Right. That's good. So let's talk a little bit about the lead up. Not necessarily. We'll get to the tool in a minute, but I want to explore your journey because it's a process, right? It's a journey, right? You probably were, going along your path quite nicely, and then you probably hit a problem. Typically, what happens when people create something, they've got some sort of an issue. They look around themselves and they see if there's a solution, and if there isn't one, they'll make it, right? So, is that sort of what happened with you, or lead me through that thought process?
Okay, well, it's not entirely that. I mentioned I do have young kids, and which means I have usually an hour and an hour 30 at night when they're asleep that I have a free time, and I don't watch TV. I don't read a lot. I like coding, so I usually have a project to keep me busy. So this project is what has been keeping me busy for the past years. Um, but originally the reason why I started it, of course, there was a reason. It was not just to keep me busy. Is as I mentioned, I work as a control engineer for electrical motors. Permanent magnet motors, the one you'd find in the car or a heavy vehicle. And we had similar tools to what Scrutiny is doing. And we used those extensively, like on a day-to-day basis. Everybody had them. The engineering team were working with them. And those are, I could say, common in the automotive industry and aerospace industry. But whenever I talked about those kind of tools, like the runtime debugger approach or debugging through instrumentation, to people that are not in the automotive industry, they would generate. I would always get the same response. They would go, "Oh, that's a good idea. I didn't know you could do that." And then I realized that it was really only known to those two industries, and all the other industry didn't have a tool that do that, right? Because you can find like the vector product can do something similar with XCP and the A2L file. But if you go, for instance, into the world of, I don't know, drone controller, well, they make their own in-house tools. If you talk to IoT people, they make their own in-house tool. They don't have, and I searched and I found no open source runtime debugger. I found there's a lot of like very expensive alternative or free alternative that are bound to a specific brand of CPU that works with a specific environment made by a semiconductor company. So I said, that's missing.
Right.
So I started with a proof of concept, showed a couple of friends, I got a good response, and then I said, all right. I kept going, and we're here 4 years later, and it works quite nice. And I even have few users. There's been a company in the Netherlands that are starting to use it extensively. Like they're converting their like internal tool chain to all based on that tool. So it's a sign that it serves a purpose, right? And that company is not in the automotive. I think they do heat pumps and like industrial stuff.
Yeah. So that's great. So it's a 4-year journey. You're here now. It's constant because software is an evolution. So you're going to constantly evolve it, get feedback from customers. So with that in mind,
I don't want to call that customers. It's an open source project, right? It's all free.
yeah, sure. Yeah. You're
So I
right.
just
You're right.
and it's
Yeah,
even
it
it's even
users.
published with
Let's not say customers. Users, right? User feedback, right?
feels more adequate.
Yeah. User feedback. Okay. So with that in mind, so with one of the questions that I had, that I thought would be interesting to ask you is, I think the audience would be interested as well, is what's one of the most weirdest kind of intermittent bugs that that you've come across that your tool has allowed you to identify more quickly or easily?
I can find a lot of examples from my previous jobs where I wasn't using Scrutiny, obviously, because it didn't exist at that time. But with a similar approach, I could give you examples. Well, I worked a lot on power converters, and whenever something goes wrong with a power converter, it always translates to an overcurrent condition.
Right.
Almost all of the time. So when you get an overcurrent condition out of nowhere, you want to know what went wrong, right? So you have to, with a tool like that, you can ask the software to monitor for an internal variable. And whenever the overcurrent bit is set to true, then read all the sensors, all the control output, control input, and then you plot a graph and you say, all right, okay, my sensor picked up noise right there, right?
Yeah.
So that's the kind of problem you debug with a tool like that.
Okay, so do you marry that up with an oscilloscope or a logic analyzer or something, or is it just the tool will figure that out?
Definitely, the tool is enough. Well, if you bring down the problem to the hardware level, you can always use a scope. And actually, there's a feature in Scrutiny where you can synchronize the software with the scope. So if you get an acquisition of your internal variable, you can sync that with the electrical input. So that's nice. But from my perspective as a control engineer, 99% of the time, the software feedback was enough.
Okay. Well, that's good to know. All right, I'm just trying to follow a format here so we can keep everything on track. So you've got the tool. It's a 4-year journey. Where do you see that? Obviously, do you have like a roadmap, like or a feature list or something?
Yeah, well, I have lots of ideas, way more than I have time to create them. But what I do is each time I think of something, I make an issue in GitHub on the repo, and I just add a feature. Okay, that I have my backlog of feature that I put there. And obviously I have even other ideas that I didn't put in the backlog because it's like further down the road. But I have my vision of what the tool should be, and that's generally that's how I present that. I'm making the tool that I wished I had, because I've used several tools that work with the same principle as Scrutiny, and I just pick all the feature I like from all of the software I use, and I make one open source. So
do you use what language are you using to build the tool?
Well, the instrumentation part is in C++ because that's for the embedded software. But outside, everything that is on a PC, the server, the client, the GUI, it's all in Python.
Okay. And are you using any vibe coding or copilots or AI to help you with the coding, or is it just
zero? I am not yet converted to that.
Okay. Well, that's fair enough. Sometimes
I know it's very trendy, but I do believe
trendy.
that nothing beats hard work.
No,
Taking the time to think the thing through.
Yes, I think you're right. I think it's too early as well. I think it's early, but I think there are companies doing this. There's a couple of companies recently that launched that are trying to do what things like Lovable and all these kind of companies have been trying to do in the SaaS world. There's a couple of companies that have just launched by a couple of young blokes that are trying to do the same thing for embedded. But we'll see. That jury's out. Now let's talk a little bit more about the tool.
Yeah.
Can we? Okay, so what are the biggest hurdles, right, that you've faced when you were developing the tool? Were there any kind of like roadblocks that you hit along the way that really got you
Yeah, I
scratching
think
your
the
head?
biggest issue I had was the graphical interface.
Right.
It's always a well. I tried to, initially. I tried to like use the modern tools. So I asked around what's the latest trend, and I did make a couple of iteration web-based. I've been convinced that I should use Electron and React and all those stuff, which I learned just to eventually just scrap that off and start from scratch with Python and Qt. And then everything started going well.
Right. Okay. Qt. Okay. Open source again. Open
Yeah,
source to the rescue.
and very structured.
Yeah.
Uh,
So what do you think about this movement, right? So because I've been in the game for a long time, and when I was in the embedded game, when I first started, it was all closed source, right? The tools were there was no such thing as open source. It didn't even exist, right? So we used to buy compilers. The only thing that was open source were the GNU tools, right? I remember the GNU tools, the C compiler and C++ compilers. They were the only ones that, and the GDB debugger, but that was all serial debugging and stuff. But those were the only open source tools. But the others were all closed source, and they were expensive. You had to buy, a physical JTAG debugger, or I used to use ICE as well for the physical debugging, but they were all coupled to a on-screen, obviously, a Windows-based debugger. But of course now we've got so much choice that sometimes you're overwhelmed, right, with the options. You got open source, you got closed source, and the open source tools are very, very good. Obviously, a little bit of work for people who are not, technical. They have to learn it, to install it and use
of
it and
course.
so on. But that's where you pay, I guess. That's where the price. Whereas with the closed source, it's kind of been done. But even with the closed source, though, sometimes there are bugs and issues and stuff like that. You still need to get support. And so, what are your thoughts on where we're at the moment with those two avenues for developers?
I wouldn't. I'm not sure what to answer to that. What are my thoughts? Um, I don't know. I don't know. I compose with what's available.
Yeah. Have you used many closed source tools? Have you used many paid
Yes.
tools? Yeah.
Yeah, several. Very often the the advantage of closed source is you get support when you have an issue, of course.
Yeah.
But often
Yeah.
it's not. Well, I can say for sure that it's not um, a vouch for quality, though. I've seen a lot of closed source software that were not that great and were easily beaten by what you could find in the open source world.
Yeah.
But yeah, you can't just make a call to the technical support and say, "Hey, I got that issue. Can you help me fix it?" Right? You get tell. Look at the code. You'll figure it out.
Well, yes. You look at the code, but you also have a community, right? So with some of the open source, you have a community you can post on a forum. But now I think, which is even better, because I've gone through this journey myself with using open source tools and accessing forums and community. Now with AI, because of the indexing that some of these engines have done now, into AI. You can simply put a prompt in and you'll get a reasonable response and code as well, code snippets, which accelerates the process. And I've done this myself, where I've struggled with something and I've used different models, and some models have been more accurate than others when it comes to, figuring out some sort of a tweak in what you're doing. So it accelerates the deployment of open source. So I think it's going to make it a lot easier as well to deploy these kinds of offerings in an embedded environment. I think for mission critical systems, there's still a use case for closed source tools because of compliance and standards and QA and stuff like that. So that's kind of that's how they sell it as well, because these companies.
You don't pay for the software; you pay for the compliance mainly.
Yeah, you pay for the validation, the certification, and all that stuff, right? For safety.
And that's actually, if I bring back Scrutiny, like there's a communication protocol between like your computer and the device you're trying to debug with it. And I got asked a couple of times why I didn't use XCP, sorry, because it's the equivalent in the automotive industry, and it's like the de facto standard for that sort of debugging. And that's exactly what you were saying. Like I don't have to get compliant with anything, right? I don't aim the automotive industry specifically. I don't want to make money out of it, right? I make the tool. I don't have any compliance requirement. You take it or you don't. So I just make my own protocol, and much easier for me. And if you don't have any compliance requirement, you don't really care what's the internal protocol, right?
No, that's right. That's right. And of course, it's all about choice at the end of the day, right? And I think it's democratizing the industry, because when it's closed source, and we see that already with the large language models. I know there's a big open source repository of different models as well, but to deploy those models, you need very, very powerful hardware. So you're almost kind of locked into some of these closed source systems. It's kind of a misnomer. People say, oh yeah, but you get all these open source models, but then you need, beefy GPUs to be able to run like a 70 billion parameter model. So most people can't do that. They don't have that kind of money to spend on self-hosted, large language models. So they'll just use the closed source models. But I think with the embedded environment, it's a little bit different, because you don't need to have a huge investment in hardware to be able to start using these tools. But it does give a lot of more freedom to the end user, the engineer, who can then, they can pick and choose the one that they need, rather than, or even modify it. If they've got the source code, they can tweak it, they can customize it for their own use case, which is empowering, I guess, but like you said, for you, it's a labor of love, right? It's more of a labor of love. You're enjoying it, you're doing it, you're trying to serve the community, but you're also serving your own, sort of interest in self-expression.
Yeah, you could put it that way, I guess.
Yeah, because it's a lot of work, right? I mean, there's got to be some reason for doing it. So let's talk a little bit about some world use cases. Can you sort of maybe give me some examples of where it's been really useful? How it's yeah.
I did mention the power converters earlier. So any embedded software that controls something, or it's not really the kind of tool you'd want to make a driver, or let's say debug. You spoke about AIs, which is merely mathematical computation. It's not really what you need. But if you want to control some hardware, or you have some decision making, or you have sensors or actuators, understanding how those behave and following like the control process from the outside is where a Scrutiny Debugger would, or any runtime debugger can be useful. If I bring back again the subject of motor control, debugging a motor with that is actually, that's pretty much the only way you can do it, because just like the power controller, when something goes wrong, you either get a vibration or overcurrent again. And if you don't have something to look inside the software and at every internal variable and make plots of this, or of everything over time, you can't do much, right? But even over that, you can, well, whenever you're ready, we can even go further about all the feature that the software has, and it does enable a couple of nice things.
Yeah, let's do that. That's a good segue. Why don't we do that? If you can maybe give us a little demo, or show us some features, things which are quite interesting, because for engineers who know this stuff, they probably get their head around it. But coming from the creator, if you can sort of maybe share some key features. Yeah.
Oh yeah. Would you want me to share a screen?
Yes, please. That'd be awesome. Yeah.
Okay.
Okay, great. Now that looks good.
Oops.
Okay, so you're invoking the tool there, right? Yeah.
Yeah. Okay. So, well, I'm working in my development environment, but obviously when you do the install, you have like a nice icon in the start menu. You don't have to launch it by command line like that.
Yeah.
Right. So, well, I could probably show you what I have on my desk. This is how I actually, oh, my bad again. I have a lot of, no, I have this blurring thing.
Yeah. Oh, there you go. Typical engineering, a typical engineer's desktop.
Yeah, well,
love it.
I want to make Scrutiny working on all kind of platforms. So I have an Infineon board, an Arduino board, a Texas Instrument board, an STM32. So, and I test all of those.
Yeah, right. Cool.
Okay. Awesome. So what I'll do is I'm gonna run Scrutiny on the Infineon board, because I have a demo for Infineon.
Yeah.
Oh, and you might see that I am making some renovations. So that's why there's a door hanging behind me now that I have under the camera.
That's all right. Angela, I'm busy. Yeah.
All right. Okay. So what I'll do is, so a big part of Scrutiny, or a big enabler, is that it works with a server and a server client architecture. So basically how it works, you have the device that you want to debug that talks with a server written in Python. And then that server exposes the internal of the embedded device to any client that wants to connect. So when I use my graphical interface, what I do is I use a client that connects to a server. So what I'll do is I'll just start a local server for debugging. So now I have a local server. Okay. Right.
Okay.
That it just auto reloaded my previous configuration. So now you see I'm connected to a server. Now what I want to do is make my server talk to a device. So what I do is I go here and I select the type of communication I want. Okay. And I just enabled CAN communication on my Infineon board. So I'm going to use CAN and say, okay, I talk with those parameters. On CAN 0, no, that's not. I'm using a vector hardware channel 0. That should do it. So when I connect that, boom, you see what happened is the server start talking with the device with the Scrutiny embedded library. So they talk to each other. Then you see that what the server found. It says, okay, I found a device. That's the hash of the firmware. So now it knows what it is. Those are all parameters that you set in your embedded software. So the buffer size, you can put a limit on the bit rate it uses. So you see everything that is configured internally. And what is interesting is as soon as it connected to the device, it used that ID here to check into the server, check into its database of debug symbols. And it said, all right, I know that hash. So it loaded a firmware. It says, okay, this is the Oryx demo. I'm going to load that. And whenever it loads that, it makes all the internal content available. So you see in my screen, I have like those variables, and I have every variable that are in my software are now available here. I can just explore them. So what I can do is put a watch window, and I'm going to take all of them. Right? So let's see what I have in my main.cpp, and I have some variable that are jiggling around. So that's working live into my embedded software. And I get, I read the value through my CAN bus because that's what I'm using, but I can do it over serial or Ethernet or whatever.
Okay, cool. And yeah, go ahead. I was going to say, can you set breakpoints and things as well?
No. That's the difference between a debugger and like what we call a runtime debugger. Sometimes it's called a calibration tool, or what I call debugging by instrumentation. So it's when you have to put an instrumentation hook in your embedded software. And whenever that hook executes, you get a snapshot of the memory, and you see that. So you cannot look at the stack, but you can look at everything that is global or static. But generally, in an embedded software, that's enough. And if you really want to debug specifically something in a function and you want to see on the stack, you can just temporarily make your variable static, do your debugging, and put it back. And most of the time, 95% of the time, that's way enough, right? You don't need more.
Well, this is a client-server environment then. So you have a server, you have a client running on the target that's sending the data back. Yeah.
There's the embedded, the instrumentation library is running on the device. Yeah. That library talks with the server, and then that server can allow many clients to connect and have this view. So I could have a second GUI that will that will read the same data from the device.
Right, got it.
And what this enables something really powerful, because now we can, it's nice to look at those values, but there isn't much we can do, right? With those, they're just jiggling around. It's too fast. But what you can do.
So what's the overhead of the library on the target?
Not much.
Okay.
It's pretty lightweight. Just a matter of it does memory dumps, validate the parameters that you send to it. In terms of RAM, I think it's a few Ks of RAM, and in terms of RAM, it's not much. I've been able to run it on an Arduino.
Oh, cool.
It's an 8-bit microcontroller with not much memory. And there's when you compile the library, there's a bunch of flags, so you can disable a few features if you think it's too heavy. But there was something important I was saying. Because of the client-server architecture, you can have a GUI like that, but you can also have a script that talks to the server. And I made a complete SDK, a software development kit. So in Python, you can, with a few lines of code, you connect to the server, and those values, you can read and write them. So when you run a script in Python, the memory access are synchronous. So if you write a value, your script will hang there until the data has reached the device and it has been acknowledged, and then you get a confirmation back, and then your script will go down. So you can essentially run a Python thread remotely in your device. It's just that your memory access are slow, right? So this enables quite powerful feature for debugging. So you can make like hardware in the loop testing. You can make your test script. You can for instance, if you put in your firmware, I don't know, a define for test mode, and in test mode, you can override all the sensors. So you compile in test mode and launch a script that sends dummy values for the sensor, and then you can simulate out-of-bound values or glitches, or you can control them.
So
See
you
what I
could
mean?
run this. You could run this in parallel with the JTAG debugger for breakpoints and things, right? And also
Yeah,
you could,
absolutely.
yeah,
Absolutely, because you essentially, I'm not the scrutiny library is not dependent on any hardware. When you
yeah,
integrate it in your device, it's your responsibility to move the data from the library to a hardware and vice versa. So in my demo, in my Infineon demo that I'm running right now, um, you can enable it over serial or over CAN. And right now I'm
yeah,
using it over CAN. So the JTAG doesn't care about what's going on the CAN bus.
yeah. Okay. Now, so with this, so this is. Can you sort of show me? So that's the watch window. Well, what about the continuous graph and the
Yeah,
embedded
okay.
graph? Yeah.
So generally you want graphs of your variable. So there's two type of graph. So a continuous graph is um, when you want to see a value of a variable, you essentially tell the server, I want to subscribe to that variable, and then the server starts streaming the values to your client. When you make a continuous graph, you take those values received by the server, by the client, and you graph them over time.
Yeah.
But there's a problem with that because the server polls the memory by sending requests of memory dumps. So your sampling rate changes with the bit rate that is available, or if you want to watch more variable, you get a bigger sampling rate, and it can become slow. Like I could plot 100 variable and get, I don't know, 100 millisecond of sampling rate, which is not that fast if you're monitoring something that's a current sensor.
Yeah.
Um, but and then we have the embedded graph, which is another type of graph. So like the name suggests, you ask the embedded device to make a graph for you, which fix the problem of the large sampling rate. So you say, I want to watch those variable and make a graph whenever that condition happens. So it's like a scope. So you make you configure your trigger, you say I want those variable, and you do acquire and you wait. And whenever the condition happens, the library fill a buffer with your variables and then send you the buffer. So the downside you have is the length of the acquisition is really smaller because it depends on the buffer size you allocate for logging. But you get a very tight sampling rate without variation, and it's fast. So what I could do is I could make a continuous graph, and I can build my dashboard like that. And what I'll do is I'm gonna make so this is something that generates a sine wave. I'm going to put a frequency of 1, sinusoidal. I want a graph of my output, and I do start, and there you go. All right, so this is being plot live. But we can see small notches in the graph because my sampling rate is not stable because it
Yeah.
depends on the scheduling of the OS right now. And I'm running a server on Windows. Windows has a thread resolution of 16 milliseconds. So like all of that comes in play. But if I want to make a long acquisition, like debugging for minutes, hours, days, I could just log with that, or even write to a CSV file, and then would just dump to a CSV. And yeah, you can make if you make a vehicle, you could make a test run. They go on the road, launch the logger, and then when you come home, you start looking at your file. But now what we could do.
Okay.
That's about it for the continuous graph. Well, you can
Okay, just
export
one
this.
sec on that. So that's the continuous graph. So that's data that's already been captured from
Yeah.
The code on the library on the target
Yes.
is sent
Well,
that information.
that's the client that plots the data it received from the server as it's being polled, right? Because it's a round robin of all the variables. The server asks for a memory dump in round robin fashion, and the device just give them because it dumped the memory to the server, and you get them over time with varying sampling rate.
Yeah. Yeah. Okay. Okay, so I just want to explore this a little bit. I'm just trying to now. How would they, like in a real life debugging session with your tool? Because you
Yeah.
change some parameters, right? You change the wave type, You change the frequency, and so these are variables that you can change as the data on the data that's been captured from the target. Yeah.
Yeah. Well, this is variable
post.
inside the firmware, and the firmware is just because it's a demo.
Oh,
It's not
so
a
you're
real use
changing
case.
it. You're sending a command to the library to change a parameter on the target.
That's the thing. It's
Right.
almost that I'm not changing a parameter. I'm changing a variable.
Yeah, the variable. Yeah.
Scrutiny, the server knows the address of every variable because it reads the
Yeah.
debugging symbols. So when I write that, like nowhere in my code do I make that available. I just declare it in my code. It's a static variable.
Yeah.
So when I write a value here and I make it faster, I tell the server I want to change that variable. The server translate that to a memory address, and it asks the embedded library, go change that memory address and put that value inside of it. And the embedded library doesn't know what it's doing. It's just altering the memory, but you get a result.
Okay. So that's not data. That's not actually off of the board. It's just inside. It's a memory variable inside the library that's running on the target that you can tweak.
Yeah. Well, it's in the firmware. You have everything. That's my mains. That's CPP. You have every variable of the firmware.
Okay. Yeah. Oh, okay.
All the global. You can even look. We have.
So you can peek those. You can peek and poke those variables, right, from the debugger.
Yeah. See, those are drivers from Infineon. I didn't write those, but I have the values. They're discovered when I make the firmware, and I could change some register. If the register are declared in the firmware, I can just change the value there.
Right.
And something very powerful you can do is because a linker script can map anything to anywhere. You could make declare all your register structure in your firmware and attribute that to a section. And in your linker script, you say, all right, this structure goes into the memory region that has the hardware. So that makes a variable that whenever you write to it, it changes a register. And then if you do that, you have a debug symbol that says where the address is, and then you can expose all the register inside Scrutiny and just edit them live. If I take my Arduino demo, I can change the timer register and it works, and you can see actually that it goes faster.
Right. Okay, got it now. Okay. So it's very powerful then. So you could tweak a lot of things there just to kind of experiment with different parameters and change the output accordingly, particularly if you're finding a problem. Let's say you find a bug, you can go in there and you can change the variable, and then you can see the effect of changing that in relation to the bug. And
exactly.
then you can recode it in your source code and recompile. Okay, got it.
Yeah, and if I take the example of a power converter, you have generally a few stages. You have let's say I want to control a current command, and then you have a PI controller that gives a voltage reference, and then that voltage reference goes into a modulator, and then the modulator produces a PWM command that goes into a driver. So if, something goes wrong, you can say, all right, I'm going to start at the modulator stage, and then in your firmware, you cut the output of your controller so that the modulator is not being controlled by anything. And then you go directly into a tool like that, and you manually input values and make sure, okay, my modulator is behaving well, fine. Then I move into the controller and I say, okay, if I do a step input at the controller, will it go crazy or will it be stable, right? And then you can plot them.
Yeah.
So it's like I said, it's useful to debug an application level. At application level, if you want to make a driver, it's not so good, because if you have a problem with a driver, it crashes, and then you need a G tag to go read the registers. But for application level debugging, this is great.
Yeah, 100%. Yeah. I mean, you need a JTAG and a proper debugging system for a driver. So this is.
But a JTAG can do that.
Yeah.
Well, Oh, sorry, no. A JTAG can do that, but it's not the same. Actually, there's a nice tool online and that has a lot of overlapping feature with Scrutiny, but instead of using instrumentation, it uses a JTAG. It's called MCU Viewer. It seems like a great tool. I haven't tried it, but it can do visualization like that, but it uses the JTAG.
Yeah.
This has pros and cons because the JTAG is completely asynchronous, so you don't get a snapshot of the variable at every iteration. So let's say you make a controller that execute at a certain sampling rate, then you cannot have a value of each control loop because your JTAG will be asynchronous. But that's another subject. It's a different approach.
Yeah. Okay, cool. Okay, let's have a look at the embedded graph then.
Yeah. Okay, so the embedded graph, well, the goal is to make a graph, but this one behaves as like a scope. So I'm going to call it my acquisition, and I will say, all right. So in my demo, I have a task scheduler, and I have a task running at 1 kilohertz, a task running at 100 kilohertz. And actually, what I will do is I will reload a dashboard. I have a dashboard for this demo.
Okay.
Right, so I have all my my 3-wave generator. One is running in the 10 kilohertz loop, another is running in the 1 kilohertz loop, and one is running in the main.cp in the main loop.
Okay, so let's just stop there for a minute. So this is interesting. So you can save a dashboard, yeah?
Yes.
And okay, that's cool. Okay.
Yeah, you can make your debug session, save it, reload.
Okay.
Right? So
cool,
what I'll do is I'm gonna make a sample of these 3 waves. So I'm gonna just delete those. So if I want to make a graph, I add an axis. I take everything I want, like that, and I can drag them here. Oops, it's one of the, sorry. When they're in different windows, you can't drag them all at the same time.
Yeah.
And I can rename them. So this one is the 10 kilohertz. This one is the 1 kilohertz loop. And this is the main.
Right.
Now, I want to probe those at high frequency, at 10 kilohertz. I could use a decimation factor to have 5 kilohertz and 3 to 5. I'm going to use 10 kilohertz. My x-axis will be time because, and there's the difference between ideal time and measured time. Ideal time is deduced from the sampling frequency, and measured time is actually asking the device to return the time. So you can have a little jitter being measured, which you don't have with ideal time. But most of generally you just want that. That's enough. Okay, and I will put a condition. Okay, so there's a button on the board. So I will say whenever you see how I drag those? You can just drag a variable and say, okay, when this variable is equal to 1, acquire. Okay.
Right.
And you can say I want to see before or after the event, like a scope. So I want, if I put 75, that means that my event will be at the right hand side of the graph, 75% of my graph. Okay. So I'll hit acquire. Now it says it's waiting for trigger. So if you're debugging, you're waiting for an error bit to be set to 1 or a glitch on or a sensor value to go above a certain level. I didn't show you, but you have like all the condition you can need for debug, like a scope. So here I'm waiting for button 1 to be 1. So I'm gonna go ahead and press the button, and I hope I won't press the reset button. Okay, there's 2 buttons. There's a reset button too.
Okay.
So I clicked it, and those are my variables.
So you clicked that on the target, and then it sent that data across.
Yeah.
Okay.
Exactly. So every point on the graph has been acquired by the device. It filled a ring buffer with all the data, and when it's full, it just send the whole buffer to the server and make a graph. And what is interesting, see, since I sample with the 10 kilohertz frequency, I have an acquisition of 270 milliseconds, and we can see that the green sine wave is like staircases because it's updated at 1 kilohertz. So from the fast sampling rate, I can see the lower sampling rate being slow.
Yeah.
Well, I could do exactly the same thing from a different perspective. So I'm going to ask the 1 kilohertz task to do the acquiring for me. Okay, and I'll just run the same thing and hit the button again on the board. Click. I just pressed. Boom. What we see is 2.7 seconds now of data because I'm limited by my buffer size. So I have less a slower sampling rate, so I can see longer in time, 10 times longer because it's 10 times slower. And if I zoom, there's no more staircase because from the point of view of the 1 kilohertz task, everything is smooth.
Right.
See what I mean?
Yeah.
You get your values like that. So if you have, let's say,
so what are we looking at here? This is an analog signal, yeah, that we're sampling. Is that from
this is not sample. It's just because for the sake of the demo, there is a small piece of code that runs a wave generator. And I could probably show it quickly, I guess. Let's see. I have it here. Let me find my demo. That would be, yeah, the Oryx demos. Where's demos? Where's the source? Source. Okay. And I have a wave function generator.
Okay.
It's just a small function that will, based on the time delta, will update the phase and then generate an output. And it's being, if I look at my main.cpp, every loop. So that's my 10 kilohertz task, and it's running the wave generator. That's all it does. It's dummy signals just for the purpose of the demo. But it could be an ADC or any signal or something coming from the CAN bus. Anything.
Yeah. Okay.
But it's a demonstration, so I'm making those signal up.
Fair enough. Got it. Okay.
But yeah, I put a hardware in here. It can be any variable. So I could, for instance, I can say whenever the frequency is 3, make a graph and then do acquire. Then it waits for trigger, and I can change the frequency myself to 3, and then it detects it and makes a graph. And what we see is that this is 75. If this is 0 and this is 100%, we have 75% here, and we see that the graph, the frequency of the green arrow became. I'm going to hide those actually. See that the frequency became slower. So that's my trigger at 75% of my buffer.
Right. Okay. Yeah. Okay. That's okay.
That makes sense.
Yeah. Makes sense. So
by putting 75%, I see most of what happened before the trigger and a little bit after. And if I did the same with 25, I'd have like the event at the left side here, and we would see what's after.
Yeah. Okay. Sounds good.
Right. So that's the idea.
Okay. So that's the embedded graph. So we've looked at the variable list. We've looked at the internal metrics. We've looked at the watch window. Oh, have we looked at the internal metrics?
No, but that's essentially just to see how well the integration works. So you can see the number of updates you receive from the server. So right now, with those watch window, I see that my server is streaming about 1,000 updates per second. And if I'm going to just duck this one here. So if I collapse folder, my GUI is telling my server, I don't need those anymore, so it's unsubscribed. Then the server stop polling for those because there's nobody listening for those, which I have less update per second, and you see that my data rate here, that's my CAN bus load right now. And if I open those, I'm going to use more bandwidth on my CAN bus because I want to see more data.
Right, got it. So that's like a monitor, right? It's like a system monitor.
Yeah, kind of. Yeah.
Yeah, you kind of see
And
that on Linux, right? It shows you the CPU clock cycles. It shows you, the Ethernet traffic. So it's kind of like that, right? It's like a monitor. It's like a tool, a monitor system. You're
yeah,
showing data variables coming through back and forth between the
it, it tells
library
you a
and
lot.
the
For
yeah, yeah,
for example, I'm running on a 500 kilobit bus, and
yeah,
because the way it can work, not all bit can be used. It's about let me see, it's 64/100 times 500. So I have a true bandwidth of probably 290 kilobit per second. So I'm
yeah,
using maybe 25% of my bus capability right now. Um, if I saturate at the max, it doesn't cause any problem. It's just that the update rate here will start to be slower. So I could take a lot of variable, for example, put my main.cpp, all of that, put it here, open everything, and I have more data and my update rate. Well, okay, no, it's not limited. But if you put more and more and more, at some point you start to see the update happening at a slower pace. It's
yeah,
just because you're hitting a bottleneck in the transmission.
yeah, yeah. Makes sense. Makes sense. Okay, cool. So looking at this interface, it's very simple, easy to use.
Yeah.
I mean, there's plenty of more features you could put on the left-hand side in the way of uh,
Yes.
you know,
Yes, and I do have a
uh,
lot of ideas. What
yeah,
I'd like to see is to put some. What I'd like to do at some point is to have some HMI elements. For example,
yeah,
a meter with a needle, right? That goes from, I don't know,
yeah,
0 to 100, and you could
yeah, yeah,
just drag and drop a variable. So, for instance, when this variable is, like, you can have the meter plot the value of a variable. So if it's a motor, again, you can put the motor speed there,
yeah,
or vehicle, or if it's I don't know, anything that, or if you make a robot, like the angle of
yeah,
the arm, you could draw it. So I'd like to
yeah,
have an HMI capabilities. Uh, it's just a matter of coding the graphical part, all the
yeah,
backbone behind that feeds the data. It's all working. So
yeah.
I'm not that far of having that implemented actually. But there's so many things I have
Awesome.
in mind.
Well, thanks for the demo. I think this will be very useful because I actually did load it up on my Mac. I did download it. I didn't connect it to a target or anything. I haven't got around to that, but I did run up the GUI. So
Yeah.
having you run through the whole thing live, connected to a target and showing it all working, I think this will be very useful for people if they want to experiment and try it. So
Yeah,
well
actually, what I was
done.
thinking of doing is to enable some kind of virtual device just for trying the GUI. Because if you don't have a device and you haven't done the integration, you open the GUI, you have this red, and you don't know what to do, right?
Yeah, yeah, oh yeah, 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 for sure. Yeah. I think, I don't know if you've got a YouTube channel or anything, but it might be a good idea just to maybe just throw some demos up. It's always good to reference them. When you reached out to me, I was happy to promote you to my community because it's definitely it's down our alleyway. I mean, that's what we do, right? As engineers, meta engineers. So any tool that helps with that, that's really handy. All right, Pierre. Look, let's keep moving. So
Yeah.
let's because I've got a few things to sort out here, but let's just finish up. According to our little, we have a little agenda here. According to our agenda, so basically, I guess what I wanted to really pick your brains on, Pierre, is also on. Yeah, you might want to disconnect this one. I don't know. It's up to you. I think this is fine. Okay, so the questions that I have here that I thought might be useful for the community is, and actually I put it out there. What's one thing that you wish more embedded engineers understood about debugging? Is there? I mean, there's all levels of debugging. There's hardware debugging using scopes and logic analyzers and all that. There's that element of debugging, hardware. and firmware. Then there's the application layer of debugging. You're kind of more closer to that than the actual device driver, close to the bare metal. But in your experience as an electronic engineer and writing firmware now and you know these tools, what is it, that one thing that you come across that is kind of like a fundamental that people kind of overlook, but it's critical to the debugging process?
Well, I could once again point out the tool we just looked at. I think using a runtime debugger like that is not like a JTAG debugger, it's a lot of gain for a really small effort. It's really worth it once you are used to that. And like I said, most of the embedded developer I interact with that are not from the automotive industry. They are not so much, I would say, aware or don't have the reflex of using a tool like that. So yeah, instead of building something in-house, custom that you have to maintain, I would rather see effort put on an open source project like that can just grow and grow and grow instead of dying because the guy who made the tool left the company. You know, it's a story we all know.
We know those stories. Yeah, go ahead.
Yeah, so it's not really, I'm not sure if I answer your question. It's not really a fundamental. But if I want to talk about fundamentals, really how I'd say how the object file are structured and like how the debug symbol works, those things. I had to learn them in depth for making that software, and I learned a lot, obviously.
Yeah. And okay.
It's worth it.
Makes sense. What about a mindset? I mean, I know we talked about the engineer's mindset, you know, the sense of curiosity and wonder about the world and trying to take things apart to try to understand how things work. What other things you think a good engineer mindset?
Every role I had, there's a thing that keeps coming again and again and again, and it's when you debug something, dig to the end, right? I'd say never accept a fix if you don't know the root cause, which probably seems obvious when you say it, but in practice, when you get the thing when the thing works, it's easy to say, all right, it's working. Let's keep moving, right? No, dig. You never know what you find. I often find issues that were deeply nested somewhere else because I dig for a problem that seems trivial. So I think the good mindset is just like do the mental effort of, okay, I'm gonna go down the rabbit hole and see what's behind that. And I have countless stories of surprising finding that people did while just digging further than they were supposed to.
Okay. So I think that's to do with having courage and a fearless mindset, right? It's like, just do it,
like that.
You know, because that's another thing that stops people. Oh no, I don't want to go down there because it might be unsafe, or you know, I might not be able to understand it. So I get having that sort of brave kind of mentality of okay, well, let's just let's get into the weeds. Let's just really get down to fundamentals, right? First principles, like Elon Musk would say, first principles, where you try to understand the root cause, like you mentioned, but that might mean that you might have to get your hands dirty, and so that's very important, 100%. Yeah, go ahead.
Well, there's a little story that came to my mind, and I could, if that's fine with you, I could take 20 seconds to tell you about it. There's a good example of that is we once had in another life EEPROMs being given back by the customer, and the EEPROM wasn't working, and the analysis showed that it was simply burned. and the reflex of people were, okay, we're going to change the EEPROM. But the thing is, it went out of the production line and it was broken. So the assumption was, right, somebody touched it, it has been burned by ESD. But I look at the failure mode and how it failed, and we found that the EEPROM had mirror addresses. That's how it failed. Like there was an electrical overstress, but when you wrote a memory cell, it would write more than one at a time. But the question then arose, why didn't we detect it at the production line? Then I talked about with the testing guy, and we found that the test sequence wasn't able to detect that failure mode. Right. So by digging, we now fix a production line so that that wouldn't have happened if you just said, okay, well, this is a defect, replace the part, move on. No, you dig further and you find stuff.
Yeah, yeah.
And then that created a process of updating test sequence in all the production line everywhere in the world, with people working overnight. So worth it.
Yeah, but you're 100% right there, because there's lots of quirks in electrical engineering, that have not been taken into consideration as test cases, and they only come up after the product's been in the field, and even the actual individual components themselves. There's some sort of quirk or physics quirk that comes up. Because the actual tolerances sometimes are marginal, they're borderline, and that enough borderline that, in a real world situation, given all the electromagnetic forces and everything that's around you, that borderline might be so significant that it might, give you an unusual effect, which only appears later on, which is exactly what you found out. So. But having that sense of trying to not just accept the status quo, if I'm understanding you correctly, and just dig in deeper and really find the root cause, is a particular mindset. Yeah, I call it the detective mindset. People who are good at debugging are really they're detectives. They're seekers of truth.
I like that too. And I could make a parallel with, when you brought up the subject of LLMs and generated code, vibe coding. That's the exact opposite of what I'm saying right now. That's I don't get into that boat. Personally, I don't like it. It brings people to stop making that extra effort, and I'm really afraid of that, because it makes. Well, I don't want to sound offensive, but it encourage you of being lazy, which I don't like.
Yeah, I think also what it does, it creates another layer. So what you and we're at the root layer, the physical layer. We start there, which is the physics that creates the electronics around us, and then there are other layers on top of that. Then you got the firmware layer, and then the software layer, and then you got the LLM layer. So what happens, and I think this is going to happen, because there's a lot of promise that these LLMs the companies behind them are telling societies that, hey, you don't need to code, you don't need to know about physics, you don't need to know about all of this other stuff that you went to university for 3 years to learn. Forget about all that. Just use a large language model, because just give it a prompt, give it a voice prompt, or give it a text prompt, and it's been trained on all of that data. All you need to know is define a problem. You just need to tell it your problem, and it will give you the answer. The challenge with that is, yes, that's great in a utopia, but when you're dealing with real physics in the material world, you need to know fundamentals. And because if you don't know fundamentals, let's say you have a generation of engineers that don't know fundamentals, they won't be able to understand. It's like a foreign language. They will not be able to go down to the grassroots level and figure out the root cause, because they wouldn't know where to start. They will have to rely on some third-party technology, which in this case is artificial intelligence. And so there is a danger of that. And I think we're heading in that danger, into that world, because I think what we're already seeing is the AI is becoming normalized. normalized, right? In the sense that people are accepting it. I mean, I use it every day, right? I mean, I use AI all the time for my work because we use it for data processing, but we're not down there at that level of engineering detail that you need because we can get away with a lot of stuff, right? I mean, if a prompt, if the output of a prompt, even though it looks right, isn't right, it's not going to, kill someone, right? It's just an error, right? But I think the more reliance we have on this tech, and the more sophisticated it gets, there is going to be this tendency to get lazy because human beings, we tend towards laziness, right? So it's kind of resisting that laziness pull, which is inevitably going to win over. It's inevitably going to win over because we all lean towards convenience. That's why we have so much commercialism, and because people always try and sell us products and services to make our life easier, right? It's always sold in the guise of life can be easier, right?
I could argue that my life wouldn't, any engineer life isn't easier when you have a whole lot of technical debt that you're carrying because your software created
the debt,
code that mostly works, but all right, it was fine. You kept building on top of that, and
I mean, if you're building an app, it mostly works. It's fine enough. It's good enough, right? If you're building a SaaS app, it's good enough. But when you're building a mission-critical embedded system, it's not good enough, right?
Well, I suppose you've heard of the recent fiasco of the T application.
No.
Well, I'll invite you to read on that. Exactly that. It's a huge fiasco. That's what happened. Technical software that appeared to work with very weak fundamentals led to really bad consequences.
Well, there was one. I mean, even with the app, even in the app world, there was a Vive app that was coded by Vive with AI. It's all purely coded. It's basically front end, back end of a mobile app. It was all coded by AI, and it got hacked. And this was like a social networking app, some sort of dating app or something. And,
we're talking about the same thing.
Oh, we are talking about the same thing. Oh, okay.
It's called T. The name of the app is T.
T. Of course, it's called T as in T. Yeah. And
that's what I'm saying.
All the data, it was all released to the internet, and so. Yeah, I mean,
government ID saved into a Firebase storage, no password, no encryption. It worked.
No encryption. Yeah.
Wasn't well designed.
No, that's right. Because a lot of these people that are now Vibe coders are people who are entrepreneurs. They're not technical people. They have an idea. They're a business type of person, and they don't have a coder. They don't even have a technical co-founder. They just basically use AI to do the coding, which is great in the sense that you get stuff into the world, but then there are consequences of that which come back to roost later on. Now, Pierre, look, it's been a pleasure, my man. I think we can close off now. Before we do go, though, obviously I want the audience to know how they can find you. Obviously, you got a GitHub repository. You can find you there. You got a website as well, right?
Yeah, the project has a website. It's called scrutinydebugger.com. From there, you can find demos, like video demos. You can find a link to the GitHub. The GitHub has obviously the software, but it also have demo application that you can run on development board. I showed you already a couple of them.
Yeah.
As of now, I have a demo for Arduino and Infineon RX. I think the entry point to get involved with the project is the website.
And how do they get hold of you if they want to have a conversation or get to contribute to the project?
Well, to contribute to the project, I'd say open an issue on GitHub. I will reply. If you open an issue in GitHub, it will ring in my pocket, and I will look at it right away. And you can find me, obviously, on LinkedIn. I have a couple of accounts that I'll use the same username, so I'm easy to find.
Great. Well, I'll link all of your socials in the video anyway, so people can reach you there, and also the GitHub repositories. Look, mate, it's always a pleasure to talk to engineers. I mean, you're obviously, like I said, this is a labor of love, and this is what's so lovely about the engineering community, that they do a lot of work A lot of work. I mean, we know this about Linux, right? I mean, it's all, individual contributors. And I think this is fantastic about the open source community, that people can express themselves, through their work and it be recognized by millions. So well done for supporting the embedded community. And I'm sure people will reach out to you and say their thanks and give you their stories,
Hopefully.
even when they've used your tool. Hopefully they'll share their stories.
Yeah,
With
that
you.
then right now my biggest issue with this project with Scrutiny is that I don't have much visibility. Because I know the tool, I made a great tool. I'm sure of it. I believe in it. It's just that I don't have much reach. I would need to go into convention, but the convention are expensive, and I'm not affording that with my personal money, right? So I try to be noisy on social media.
It's good.
Try to make
I
it
mean,
seem.
hopefully you might get an invitation to one of these trade shows to do a talk. I think that would be great.
Yeah, actually, I did a talk last year in a show in Montreal, but it was a show mostly targeted to the hacking community, so I didn't quite have the right audience, I think. But yeah, I did. Yeah, you can actually, if you go crawl into the demos, there's a link to the talk I gave last summer about the project. You can find it back here. But I'd love to repeat the experience in a show targeted to embedded engineer.
Well, there is actually, I'm actually connected with a bunch of guys in the US that run these online training webinars for the embedded community, and they invite speakers. I've spoken on it once or twice, but I think it was once. They invited me again, but I was too busy. But they, I'm sure they will get a lot of value. So I'll hit them up and let them know about you.
I love that. Yeah.
And I'll send them the video, and they can watch it, and then they can reach out to you and get you on their platform.
Yeah, there's two things. There's the software itself, how it works, how it can be used, but there's also the approach of debugging with by instrumentation. That is something not everybody is used to. When I showed you the software, I saw that you were asking questions not only about the software, but what could you do with that, right? And that people don't know. And once you understand what you can do with a tool like that, now you get interested in a specific tool, right? So I think there could be training about debugging by instrumentation, like the concept, and after Scrutiny is just an option.
Yeah, I think that show and tell is definitely the way to go, because people they'll it's a nice shiny new toy, but if they don't know how to use it,
Exactly.
then they'll just use a little bit. They just do the surface, and then they won't go into the weeds, and they'll miss out on the real essence of the tool. So to show that to them through walkthroughs and all that sort of stuff is a really good way to get the word out. But Pierre, it's been lovely, my friend, to see you.
Pleasure.
I'm going to come. Well, next time I'm in Montreal, I'll hit you up and we can go and get some nice French food or
why not?
Whatever. But it's always lovely there anyway, so it's really nice. Yeah. But I do like Canada. I think Canada's great. People are lovely and warm. Weather not so much, but that's how it is.
It warms in the cold.
There was in the cold. All right, my man. All the best. Nice to see you. Take care of yourself.
Have a good day.
All right, my man. Cheers. Bye-bye. Bye-bye.